Good morning. Good morning. Thank you for joining me. I can see you saying good morning, and I can hear you saying good morning, even if you're not attending live. If you're watching this later, I can see and I can hear everything. I hope. No, I don't know. Okay, because we know, yes, I hope you know the quantum physics. Yeah. Things that they are observed, they behave differently. Yes, I mean, this is just a broad statement, but that's true. When we're not observing the photons, or if we're not observing things, they behave totally different than when they are observed. Yeah. Yes, interesting. That's we don't want to know and observe everything. No, because things are changing. Okay, let's start. Let's observe a couple of things. Let's actually analyze, let's calculate, let's rate the change. Okay, that's what we will do. The plan is to cover just 2 sections in chapter 3 this week, and the next week we will take the first midterm test, okay? And the midterm will actually include everything, chapter 1, 2, and these 2 sections, 3.1 and 3.2. And yes, we have comfortable situation because we can cover today 3.1 and we can cover tomorrow 3.2. That's what we will do in this chapter. We will introduce the magic word derivative. Okay, I know that some of you probably know. Do you know what derivative is? Yes, okay. Okay, I can see some thumbs up. Okay, that's me. We will definitely define. Hopefully, yes, hopefully we will like clear the concept out. That's yes, I will uncover the magic word derivative. And as I mentioned in chapter 2, talking about the tangent line, that section 2.1, in chapter 2, we just talked about the limits. And we kind of like left the slope of the tangent line concept for a moment, and now we will take it back. Okay, let's see what we have. Okay, actually, I do have this. I just prepare a couple of questions for my students to making sure that the answer for all of them is yes. Okay, then you're going to be more than successful in this class and in any other class. Okay, that means this is in the notes. That means you can check the lecture notes or you can pause the video and you can try to answer all of these questions. And most of them, you have to answer yes. Okay, I really want you to answer yes. Okay, we will not read them, we will not discuss them, but you can really quickly scan them with your eyes. Yeah? Okay, let's move on. Okay, that's what we did in chapter 2, the beginning of chapter 2. We talk about the slope of the tangent line, and we figured out that we cannot really get directly, explicitly, the slope of the tangent line, and also the slope of the tangent line represents what kind of rate of change? Can you remind me? What rate of change? Because it is rate of change at one moment. Yeah, the instantaneous. Yes, could be the velocity, of course, because if it's the rate of change of distance over the time, but yes, it's the rate of change at one moment. We can see at the moment A, the corresponding value is f of a, because we're trying to incorporate this to the function. Yes, velocity, if x is time and y is distance over the time. It's like a slope, rise over run. But it's at that instant. This equation represents the average rate of change, the slope of the blue line, slope of the secant line. And that's not a problem. Yes, we can calculate. But what we have to do to get the slope of the tangent? Somebody remember? Slope of the tangent, because that's the, it's just, yeah, just, it was covered in section 2.1. Do you remember? Because we have the blue line. Take, yes, of course. Thank you, Lara. We have to take, we will still use that concept because that's algebraically, arithmetically correct. But we want that x value, that point Q, to be extremely close to the point A. Yeah, that's when we're creating almost instantaneously, like yes, teeny tiny intervals along the x and along the y-axis. That's when we're moving completely. And in order to write this down, we will use the limits notation because we know as x approaches a, x is not a, but it's almost a. We know that concept. Okay, that's what we will do. Let's look at my nice pictures. I mean, our pictures from the textbook. Q, 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 closer and closer and closer, and then we can get that instantaneous rate of change. We can rate, we can calculate how things are changing at that moment. And that's what everybody wants to know. Yes? If we can predict how things are changing at this moment, then we can predict like, yes, more like globally the situation in any fields. Yes, we know it's everybody's looking for this. Okay, and that was the statement. The slope of the tangent line is the limiting position of the slope of the secant line. Yes. Okay, and that's the formula. That's we have definition. Yes, slope of the tangent is basically, let's call it m, and it's called like this. This is rise, this is run. Difference in y's, difference in f's. Okay. Let's use this notation, delta y over delta x. Okay. And we also have to be careful because we learn in chapter 2, talking about the limits, that the limit, when we have the limit may not exist. Do you remember the situation that the limit is undefined? Can you give me any example? Because then when we have a limit, I always have to state this, that limit may be not defined, even if we have a definition in terms of the limit. Situation could not exist. What was the situation that the limit was not defined? Any? Do you remember this discontinuity? I mean, not all of them. One type of the discontinuity will give us the jump. Yes, thank you, because the jump has different limit on both sides. If the left and the right hand side limit is different, no limit. That means it could be the case. Because we may think this is a definition of the slope of the tangent. Do you think when we have a discontinuity, a jump, can we really draw a tangent line? This will be only one case. We do have a couple of more. That means let's pretend that this is the situation. Let's say 1, let's say 2. That means does this function f of x, like, does this function have a tangent line at A? Can we draw a tangent line? Yeah, it will be not possible. Yes, not possible. That's when we have this type of discontinuity, we will not draw a tangent line. No tangent line, no slope. And most likely, if we will do explicitly, the limit, not most likely, definitely, the limit will not exist. Okay, that means we can have this situation. Okay, but for now, let's look at the nice continuous curve, and let's maybe look at the question, and let's find an equation of the tangent line. We also did this question, parabola x squared at the point 1, 1, as a first question in chapter 2. Yes. But now what we can do, we can set up, yes, we can set up like a limit. We can use, we can use the limits and we can go directly to the question. We don't have to do this approximation. Do you remember what we did to get the slope of the tangent? Because we have to go through this limiting position of the slope of the secant, 1.5, 1.4, 1.1, 1.01. We have to point Q, the other point has to be closer and closer. And we were trying to get closer and closer and compute the slopes of the secant and approximate. Now we can set up right away. I mean, actually, I can maybe use point slope form, and this is slope. We just have to calculate that slope. Okay. F of x is the coordinates of Q. 1 f of 1 is coordinates of the point of the tangency, where the tangent is attached. And now function is x squared. And everybody knows how to compute this limit. What is this limit equal to? It's 0 over 0. However, we know how to find this common 0. It will be just x, but we need the value because as soon as we eliminate 0 from the denominator, we can use the direct substitution. That's when we can factor out, correct? Yeah, I'm sure you did in your notes because you're writing, yes, along with me. That's the common 0, and now it's just 1 plus 1, 2. Yes, because now we can substitute instead of x. We know it's a tool. We still know what this means. It's limit. It's a limit. But that's based on the definition of the slope of the tangent. We have a limit too. Limit exists. Of course, parabola x squared is continuous. The limit will exist. Okay, NO, again, point slope. And this is the equation. Actually, is this correct? I'm just looking because I think, no, it is correct, negative, when we distribute negative 2 plus 1, yes, 2x minus 1. And when we draw it, we actually got this answer. Okay, and the 0.11, at the 0.11, this equation is 2x minus 1, y, x, and parabola x squared. All of the labels are on place. Okay, that's what we can see. That's the definition. This is important. Right? When you will see this, you have to know that this limit represents the slope of the tangent, or in general, instantaneous rate of change of the function f of x at the 0.11. We may even do it in general, f of a, x minus a. Yes, then the point is a f of a. Actually, this is still not a definition. We need to indicate this behavior. Okay, that means this is the slope. This is the slope, rise over run. But we know how close point A and X is, and f of X and f of A, respectively. Okay, let's keep moving. Also, let me remind just the terminology. When we're looking at the slope of the tangent at the given point, we can also say that this is the same thing like slope of the curve. Which slope of the curve doesn't sound good because curve is a curve, but if we really understand that slope of the tangent is the same like the slope of the curve at the given point, we understand the calculus. Yeah, because then we really zoom in. Like let's actually see this. The scale between 0 and 2, that's the curve. Between half and 1.5, yeah, we're getting closer, almost a line. 0.9, 1.1, almost a line. And if we will even go closer and closer, it will be like a line. That means the slope is the same like the tangent, the slope of the curve. Okay? Okay, that means just don't be surprised or like confused. Oh, slope of the curve, the same thing like slope of the tangent. Okay, we've got this. And now, that equation, that definition that I just provide, the definition of the slope of the tangent, let's change a little bit, because we have to go up and up. We have to climb. That's it. We will do something. Oh, let me check what I have. Okay. What we will do, because x and f of x, we have to hold this as this is function. And since we're building more general formulas, shortcuts, and some understanding, we have to keep this notation like to indicate the function. Because if I would like to say, okay, this is function f of x, then I will be confused with this value. Yes, the point q that we always have to choose. That's what we will do. We will always have given point a, f of a. This is given. Yeah, because this is the situation. This is the instantaneous rate of change at the point A. We have to, the whole story, the whole game at A. That means this is given, A, f of A, no problem. Now, the distance that we're going away from A, I will call it h. Okay? And of course, what h has to be? Big or small? The distance between these 2 points. Please just tell me. H has to be, because this is big, yes, this is big picture, but H has to be that distance, yes, this distance, basically delta X, basically run. The distance between point P and Q, it has to be almost 0. That's when we definitely know that H goes to 0. Yes, but that distance between these 2 points, we still theoretically have, it's called H. Then if this distance is A, this distance from 0 is h, that x can be replaced with a plus h. Yes, easy, because a is given and h is almost 0. Right? I mean, we know 0 is approaching 0. That means that's it. That's the only thing. And then we did eliminate that x, that independent general variable. And if this is, just this. That means if this is a of a plus h, the corresponding value will be f of a plus h. That's it. We will see it's much, much easier for calculation. And then that's what I did. This is x, a plus h. This will stay the same. And instead of x, when we will put a plus h minus a, yeah, just adjusting this formula, we will end up with h. Okay, that means this is the same thing. Okay? It's still rise over run, it's still delta y over delta x, still definition of the slope of the tangent, but with the h notation. Okay, with the h notation. Okay, and now, yes, I typed here. And now let's look at the definition one more time. Definition, the first one, actually, that's the first one that we just have. I copy. And the second one, the same thing. The same thing. Yes, this is still changes in y, changes in x. Rise over run. Rise over run. The same is here. It's just different labels. Okay. Run. But we will use this, and we can see h must be 0 because h is that distance between point P and Q. The same like x minus a. It's a distance between 2 points, x and a. But we will have this. Okay, and now let's actually get the equation of the tangent line. Now, equation is a little bit different. 3 over x, hyperbola, 3 over x, at the point 3, 1. Equation of the tangent. We need slope, and we have point. Yeah. Oh, I have actually the equation. That's the graph. It's okay. We have to get it. It's weird form. It's not slope intercept. It's the, how do we call this? Standard form, I think. Like if we moved all of the terms on the left-hand side and eliminate fractions. Okay, let's try to get it. Equation. Okay, that's me. Again, we don't have to, but I can write point. Oh, what is the y value is 1, slope, and x value is 3. This is the equation. We can even sometimes leave it in that form, but we have to get slope. Okay, and the only thing at the moment is the definition. Yes, we have to be careful, and I mean, we have to know the definition. I will, of course, we will cover the shortcuts and we will be so fast. But if we solving question from this section 3.1, we have to use the definition. Okay, even if you know a little bit more, then we can use it after section 3.1. Yeah, if it's really specified, even on the test, on the homework assignment, that we have to use the limit definition, yeah, it's always this way. Okay, that's we can see the point is a f of a 3, 1. That means f of 3 plus h minus f of 3 over h. That's the slope. We know this is just the rise of the run. The h is almost 0 because that's the distance between point P and Q. And now let's evaluate. Hopefully we can evaluate. Are we okay with this? Let me maybe check. If f of x is 3 over x, what is f of a? Can you type? I will just check the evaluation of the function, which I think is chapter 1. Okay. Yeah, just instead of x, we will substitute whatever is here. It's the argument. It will be 3 over, no, it will be 3 over a. No, I'm just checking couple of general questions. If it's like f of t, we will say 3 over t. Yes. If it's f of, I don't know, triangle, delta, 3 over triangle. Yeah. Now, if it's f of 3 plus h, we will put 3 plus h, 3 over 3 plus h. And that means this is the evaluation. We can see 3. F of 3, yes, f of 3 is 3 over 3. It is 1. That's we have 1, and we have, just in case that we a little bit confused, then we are not. Okay, I can erase that. Checking. We're good with this. Okay, and now what we have to do, let me also remove. It's a typical limit from chapter 2. It's 0 over 0 when we do the direct substitution. We have to just simplify. Since we have like 2 fraction bars, let's eliminate, let's get the common denominator, and let's present on the 1 fraction bar, and hopefully we can cancel out some common factors. Okay, what I'm planning to do, I'm planning to multiply each term, numerator and denominator, by that small denominator 3 plus h. Let's see what's happened. When we multiply the first fraction, only 3 left. When I multiply by -1, we have to keep it, and we will also keep the denominator. Correct? Because we do not distribute. Because where is the problem? Where is the 0 that we would like to cancel out? Let me actually put this 0 over 0. The h, yes, the h is the problem. I mean, for the calculation, it's not a problem. It's a beautiful settings. Yeah, h is the problem. That's we have to find the common h, common 0, and cancel out. Okay, let's distribute negative. And please note, because we're distributing it, just algebra. And now 3 minus 3 gone, h over h, actually negative, but we have h. -1, I can use, common 0 is gone. Yeah, we can see just the limits, just the limits. And now we more than fine to substitute 0 for h. The slope is -3, 1/3, -1/3. Yeah, nice. Okay, and now point slope, and that's the equation. And if we moved all of the terms to the left-hand side and multiply by 3, we will get that form. But this slope intercept is a good form because we see the slope right away. Yes, we see the slope. The slope is actually negative. Yes, negative. And we can see it's negative. And yes, and we see also 2. 2 is the y-intercept. Okay, that's the way to use the other definition. Okay, let's keep moving because we have, okay. Of course, if we would like to find the instantaneous velocity, we will use exactly the same limit, the same procedure. Yeah? We also, I hope, yeah, we remember from chapter 2.1 that the instantaneous rate of change, instantaneous velocity is exactly the same exercise, like if you have to solve it, if somebody asks you, like finding the slope of the tangent. Yeah? If you have a model, if you have a curve, draw it and somebody said, oh, what was the speed at that moment? At that moment, you can like draw a tangent and you can even quickly like predict. Oh, I think you can think it's quite steep. Maybe 5, 10, 10, maybe 10 miles per hour. I mean, meters per second. Let's say it's a small scale, small scale. Yeah. And then somebody will ask you, oh, how do you know this so fast? Oh, it's just the slope of the tangent represents the change, the rate of change at that moment. You are so smart. Yes. I want all of my students to be the smartest kids. Yes, after you finish this Calc 1. And I hope I will see you in Calc 2. Okay, the same idea, slope of the tangent. Okay, I have a definition. If we are asked to find the instantaneous velocity, we can see we're using the same definition. I don't have to explain. We know the meaning of everything. H, of course, is the distance between 2 points. Okay, now, okay, actually, let me the next slide, finally, because did you realize, because I just, if we have to actually compute any instantaneous rate of change, we were just talking about the slope of the tangent or instantaneous velocity, but anything that is changing at that instant, some growth of population, or maybe decay, or maybe some interest rates. What do you think? What kind of calculation we do? What kind of limit we will use? Do you think we will use the same one? Is everybody using the same limit? Of course, the answer is yes. This limit, yes, calculates the instantaneous rate of change. And because it's so widely used, we have a special name. And now, believe it or not, what is the name of this limit? Who can tell me? What was the name that, yes, this is derivative. And I know that most of you knows like derivatives, all of the formulas, but formulas are easy. You can always learn. You can ask your computer will tell you everything, yes? But we still need a human, yes, human factor, human aspect in all of this connection. That means I am telling, yes, I am telling you that this limit is the derivative, okay? If you knew or if you don't know, yeah, it's good to know that this limit is the derivative. That we have a special name, and let's look at this special name and special notation. That means this limit represents the derivative of function f of x, but at the moment is at the point x equals to a. Or maybe let me not confuse you, at a. We know that a is the x, at the point a. Yes, I want to avoid that x. That means this is the derivative, but we can see is at that. We're not still looking at this globally. We will do tomorrow. We know that derivative at the given point is basically the instantaneous rate of change. That's mean, please remember, instantaneous rate of change, how things are changing at this moment. Okay, and that's the limit. From the graph, you also can really picture, like if you see the graph, picture the slope of the tangent and then predict really quickly the slope, and that will be that rate, how things are changing correspondingly to the model at that point. Okay, that means this is derivative limit as h goes to 0, f of a plus h minus f of a over h. Okay, and now we also have a special notation. We will not say is f of a, because that's wrong. We will say prime. f prime. That's the notation for the derivative. And as I indicate, is f prime, derivative of f, at the point A. That means I have to put A here, not x. We will add x tomorrow, okay? We still have to understand that this definition represents the derivative at the given point. Rate of change, instantaneous rate of change at the given point, okay? Now let's put this together. Definition of the derivative, which is exactly the same like slope of the tangent line. What is slope of the tangent line? In the calculus terminology, slope of the tangent line is called, you can just repeat the same word that it's the last on the chat box. No, yes, but shorter. What we just learned, slope of the tangent line is called, yes, instantaneous rate of change, slope of the curve, good, but in general, derivative. Yes. Everything what you listed, slope of the curve at the given point, instantaneous rate of change, instantaneous velocity. How we can calculate? We have to calculate the derivative. And at the moment, we know this definition, limit definition, okay? And this is the old one. We can see that includes x. It's still good, but we will use this one because we will actually save the x for, we will see, for to indicate general, like the variable. We will let a to vary. Okay, that's the derivative. Now I can ask the question this way. Compute, not the slope of the tangent line, which will be the same exercise, but compute f prime at 3. Oh, do we see prime? F prime at 3 for the function x squared minus 8x. We have to find the derivative of this function at the point 3. Okay. One thing that we may predict, we will use the limit definition, yes? That means let's go through the limit definition because it is important. Do you think we can get positive answer or negative answer? If I think about the curve, how this parabola, it's 0 and 8. 0 and 8, if this is 8, this is 0, this is in the middle, chapter 1. Okay, and actually 3 is somewhere here. That means this is the tangent line. That means, what do you think? The f prime, okay, I didn't type. Yes, thank you. F prime at 3 is actually also the slope of the tangent line. The answer will be negative. Yeah, we can see how we can now combine all of this small information, yes, that we just learned, and we can even predict, yes, the answer must be negative because the slope is negative. Really good, thank you. I mean, I can say, yeah, okay, we're expecting negative. If we will make some arithmetic mistake, we can always correct ourselves. Okay, let's start. Yes, because f prime is the derivative, but it's also the slope of the tangent. Let's use the definition. Limit as h goes to 0, f of 3 plus h minus f of 3 over h. Limit, always limit. Okay, we will evaluate function for 3 plus h. Instead of x, I will put 3 plus h. 3 plus h squared minus 8 times 3 plus h. And this is the first part, minus f of 3. 3 squared, 8 times 3. And we may guess, if we substitute instead of h 0, we're getting 0 over 0. But we know, we saw the tangent, we're expecting a finite number, negative finite number. Let's expand everything and find that problem. The problem at this moment, of course, because this is not a problem. It's the greatest achievement, I would say, on the earth so far. Oh, no, we do have still, but no, yes, it is. Yes, it is. No, I can't, yes. Okay. Oh, please help me. 3 plus h squared, we will FOIL this. It will be 9 and then twice 6h plus h squared. Distribute 8. 8 times 3? I mean negative, yes, negative, and negative 8h. Negative 9, positive 24. I hope I distribute everything. Now the nice moment, because we may cancel out this, and we see the common factor. Limit as h goes to 0. We have h squared 6 minus 8, negative 2. Am I right? Okay, yes, I think it's correct. And now we see the common factor even better. That's h. Let's factor out h minus 2 over h. Now it is gone. Now we can substitute. What is the final answer? Or what's the slope? It's negative 2. Yes, it is negative. No mistake. Good. That means this is the derivative, yes, of the function x squared minus x at the point 3, and also represents the slope of the tangent line, or instantaneous rate of change. Yes, instantaneous rate of change at the point 3. And we can see nice, yes. That means if you are asked to use the limit definition, look at this beautiful solution. And always carry the limit, always. Please do not think that you, I don't know, wasting time. No, 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 no. You're contributing to your growth. Okay? Okay. And then as soon as the h is gone, we may not write a limit. We don't have to. Okay. That's important exercise, yes? Important exercise. Finding a derivative through the limit definition. Okay, and now, I have solution, okay. Oh, we have another one, the same thing, find the derivative of the function x squared minus 8x plus 9 at the number a. Oh, wow, that's, we have to carry the general constant. It's fine. You can try to do this. Okay, try to do this on your own. This is the answer, because if a will be like a number, I don't know, 3, 4, or so on, we can just substitute and get the slope of the tangent. And actually, my next question is, find the equation of the tangent line to the same parabola. We can see x squared minus 8x plus 9 at the point 3, negative 6. That means a is 3. If a is 3, can you tell me what is the slope? It's actually similar. Wow, I didn't even. The slope, what will be the slope? Because this is the slope of tangent, derivative. And if a is 3, what is the slope? Let me use m. Yes, I know we have to just repeat the same. 6 minus 8, negative 2. Okay, and now it's a little bit different parabola. We can see because it's shifted 9 units down, the previous one. And yes, it's negative 2. Oh, too fast. This is the equation of a tangent line. Point slope, and you can see, I just use this, I know from the question 4a, just in case if somebody will ask, how do I know this? And we can see that we did get this, we calculated slope, and then we have a small application. Okay. Okay, let's keep moving because we will have, okay, and then I have another exercise. Find the derivative of the function square root of x at the point 1, 1. You can try. You will have a square root limit. We know the process, conjugate, and so on. I have another function, another like polynomial, x minus x cubed at the point 1, 0. You can try. Check the solutions later. I have another one, hyperbola, 1 over x squared at the point negative 2, 1/4. Will the derivative be positive or negative? we have to find the derivative. Derivative is f prime at -2, because this is a, -2. And this is also slope of tangent. Tangent line at the point -2. Do we know the graph of 1 over x squared? Section 1.1, hyperbola in the first and the second quadrant. And -2 is here. That's me. What do you think? It will be positive or negative answer? Positive. But do you think will be big number or relatively smaller? Because we see the position not really steep, small, yes? That's what I want. If somebody asks, oh, how this model, because we may call the equation the model, how this model is changing at -2, you will say not much. It's like a small, it's positive, yes? It's like increasing. Yes, it's increasing, but slowly. Yes. Oh, but then at some point it will increase fast. Yes. Okay, that's what you can see. That's what I want you to understand. Any other formulas you can learn in a minute, but understanding, yes, it's important. Okay, you can do this question. Oh, I have another one. Oh, a little bit maybe complicated, but you can do it. You know the process. You know the process. Okay, we don't have to do it together. Okay, now let's look at this one really quickly. Find the derivative of the function f of x equals to 5 at x equals to a. First of all, let's think, what is derivative? What is this function? Because we may use the limit definition, but let's combine again all of the concept. F of x equals to 5. What kind of function is this? It's a constant. What is the position of a constant line in the xy plane? If we will draw it, what's the position? Constant function, how we draw it? It's a line, horizontal line. Excellent. And now the final question, what is the slope of the horizontal lines? 0. That's when you will see a constant, but only constant, only constant. And if somebody will ask, oh, how things are changing? 0, they are not changing. The derivative of the constant is always 0. That means it doesn't matter what is the x value. Yes, if this is function 5, this is a, we can see the slope is 0. Could be 2, 3, 4. I assume that this is 1. Always horizontal, slope of the horizontal lines are 0, because tangent line to the line is the same line. We actually know tangent line to the slope is also the same line in that small scale, at that small scale. Okay, that's in, please remember, the derivative of the constant is 0 because of the horizontal, because of the slope of the horizontal line, not because of any other formulas that we may fit, and we will. Yeah, always answer because of the horizontal position, slope of the horizontal 0. Okay, that's how I will recognize that you are my student. Okay, I have a limit definition. Yeah, 0. It's maybe, I don't want to, yes, really go deeper, but maybe it is confusing because you will probably tell me, oh, it's still 0 over 0. But we got exactly 0 on the top. We can see no h. It's like exact 0. It's not like that common factor that is also approaching 0. This numerator doesn't really include h. And if we see something like this, we have to think that h is tiny number, 0.001. 0 over tiny number is 0. 0 over even more smaller number, it will be 0. Okay, that's the interpretation. And now just general. We don't have to have really 5. We can have any, I choose B. We can have any constant function. Always the derivative is 0. Okay, That means for the constant function, derivative is 0. Okay, we actually know first formula, but I don't want called formula. I want you to understand. Okay, now another interesting derivative. Find the derivative of the function 5x plus 1. That means this one is not a constant. The point A, any point also. Let's think. Do we know the equation? What's the equation 5x plus 1? This equation represents what kind of curve? It's a line, linear equation. Yes, thank you, Lara, thank you. A linear equation. What is the slope of the line? We know right away. What's the slope? Slope is that coefficient of x, it's 5. Oh, Brian, I think you mean 5. The coefficient of x. Yes, the coefficient of x, yes, yeah, yes. The coefficient of x, 5. Okay, that's what is the derivative of the linear function? Of this function, 5x plus 1, what's the derivative? 5. It's always the slope. And also, please don't think about any formulas yet. No, for the constant, horizontal 0, and for the linear function, it's just the slope. That's the derivative. Because it's constant, it's not changing. Yes, it's going like the same slope. It's continue as x goes to the infinity. We may use the definition, or the limit definition. Oh, you can check later, we know, and this one has no problem because this one we cancel out 5. Of course, we knew it. We knew it. That means slope of the line, it's actually the derivative slope. And could be any function, we will always get m. Actually, I like to say derivative at any point. Derivative at any point. Okay, and I have nice statement that when we have a linear function, always derivative at any point will be that slope m. Oh, no, Reese, okay, because you're asking, oh, okay, please, because I was looking again at the assignments. For all of the assignments, please wait until the tomorrow session, because this section 3.1, it's a beautiful introduction. Yes, I want you to understand the concept. Tomorrow, I will provide more formulas. That means the question that you ask about the exponential function, e to the x, I will show you tomorrow. So easy. Okay, so easy. That means please wait, because I think most of the assignments kind of like refers to the section 3.2. Because 3.2 is more like tools, and we still have a couple of definitions, but it's like more tools and more applications. I mean, please wait until tomorrow. After tomorrow's session, you can solve everything. Okay? Okay. But I just want to stress out horizontal line and the and just the line. Not horizontal, with the slope different than 0. That the slope is the derivative. Yeah? If you are asked, you will know right away. Okay, let's keep working. Okay, now, because we still have a couple of important things, and then we will go to more formulas tomorrow. Okay, another exercise. Having a function absolute value of x, we have to find out if this function is differentiable. Differentiable means the derivative exists. Yes, I think it was in the definition. If the derivative exists, theoretically that limit exists at that point, then function is differentiable. And just at 0, you may still answer this question like collecting all of the information. Because we know, let me write maybe this. This is a definition of the absolute value. If x is positive, it's just x. If x is a negative, it's negative x. And we can see this is x, that line, and this one is negative x. And now I can say y prime. This is a little bit more general. This is more tomorrow, but let me ask you, because you can answer. What is the derivative of the function x? What's the derivative of x? Yes, one. Why? Why is one? I have to hear this. Why is one? One is the correct answer. One. Oh, we just said question 10, exercise 10, because that's what I will ask for the entire semester. I will ask you why the derivative of function x equals to 1. Oh, somebody, please tell me. Because of the slope. Thank you, Nathan. Thank you. Not because of, I know probably you're thinking about some complicated formulas, adding, subtracting. No, 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 no. Linear function, constant slope. Yes. Thank you, Reese. Thank you, Nathan. Thank you, Brian. Yes, the coefficient of, yes, exactly, Lara. Yes. Okay, and now that means I can say y prime equals to 1. What about that y prime? What about negative x? What's the derivative? What's the derivative of that line? Y equals to negative x. The same thing, right? Negative 1. Of course, slope. Slope is negative 1. Yes. And I can just say this. Yeah, that's we have no problem. Derivative is 1. Derivative is negative 1 because of the slope. But we may have a situation exactly at 0. Okay, and I use the definition. Let's see. Oh, I didn't type. I typed on the other. Let's see. Let's quickly do it. Derivative at 0. 0 is that a. Okay. Oh, I cannot. This is a. That's we have limit as h goes to 0, f of 0 plus h, because now we have to be cannot write. Let me say f of 0. Okay, over h. That means 0 is a. H also approaches 0. But let's see. Limit as h goes to 0. Absolute value of 0 plus h. Absolute value of 0. Just the limit definition. Limit as h goes to 0. This is absolute value of h. 0. Absolute value of 0 is 0. That's we end up with absolute value of h over h, which it is 0 over 0. But we don't know, yes, we have to split for h being 0 positive, like on the right-hand side, and h approaching 0 from the left-hand side. If h is from the right-hand side, it's positive. It means the limit is 1. If h is from the left-hand side, we have to put it this way. We remember absolute value, negative 1. That means, do we see what's happened? One-sided limits are different. Then, do we have that limit? Does this limit exist? The limit does not exist. D and E, does not exist. Yes, that means that's the situation. At 0, function is not differentiable. Derivative at 0 does not exist for this function. But do you see what we have with respect to the shape of the function? What we have? We have that sharp turn, corners. And do you think, can we draw a tangent line? At that green dot, can we draw, like when we have this sharp corner, tangent line, like we want to respect the definition, the meaning of the tangent, slope of the tangent, the same like slope of the curve. We will never draw that tangent line. Sometimes, which of course is the mistake, will always be 0. No, not 0, because that's actually, yes, sometimes we think that this is a tangent line. No. Because when I zoom in the tangent line and the curve, we will still have that sharp corner. Tangent and the curve, they have to be indistinguishable. We cannot distinguish the difference. If I draw maybe line like this, yes, I can draw line like this or like this. Tangent, because I can theoretically draw a line that is touching, but it's not exactly, yes, the meaning of the, doesn't really represents the meaning of the definition, because we will never smooth out, even if we will zoom in so like closely. When we see these sharp turns, sharp corners, cusps, kinks, no derivative at this point, because no tangent, no slope, no derivative. Okay, that's, please remember, when you see this, yeah, these sharp corners. The same when you see the model, the function, and you see this sharp corner, you can say, no, we cannot really predict, or we cannot really calculate the changes, yes, at that moment, because we can see it's like this and like this. It's rapid change. I mean, we may predict the left and the right hand side, but not exactly at this point. Yeah, at the sharp corners, derivative does not exist. Yes, the derivative, we can say D and E, yes, undefined. Yes, yes, good. Okay, and then let's actually, yes, finish, because I don't wanna rush. I have another exercise. We will carry on with this section, because I have just couple of information, just couple, and then we will jump to section 3.2. Okay, but please remember, let's finish the session with these sharp corners. Okay, no derivative. And remember, derivative of the linear function and the horizontal, the constant function, which is also linear function. Okay, thank you very much, and thank you for your participation. As always, I'm so happy to have my students in the live classroom, and join me tomorrow. Join me tomorrow. Okay, see you later. Thank you. Thank you. Thank you. Thank you, Brian. Thank you, Laura. Nathan. Reese, Fatuma, thank you.